Hello, everyone. I'm very happy to have Roshan presenting his talk today. He is a PhD student at IIT Bombay, advised by Rohit Gurjar. He works in very many areas, including algorithms, matroid theory, fair division, and he's also a recipient of the Prime Minister's Research Fellowship. So, Roshan, take it away.
Yeah. Hi, everyone. Thanks, Raghuvansh, for organizing this talk. So I will be talking about our recent work, which is titled Equivalence Testing of Principal Minors. And this is joint work with Avnil Chatterjee, Sumanto Ghosh, and Rohit Gurjar. So first, I will start by defining what is this problem of principal minor equivalence testing. So here is the notation that I will use throughout the talk. So given an n cross n matrix and two subsets S and T, this A S comma T represent the submatrix of A such that the rows of the submatrix are indexed by the set S and the columns are indexed by the set T. And if S and T are same, then we represent it by AS. That is the principal submatrix corresponding to set S. And now the principal minor corresponding to set S is just the determinant of the principal submatrix corresponding to set S. And in the problem of principal minor equivalence testing, we are given two matrices as input, say A and B, and the goal is to check whether all principal minors of A and B are same or not. So since there are 2 to the power 2 raised to n subsets possible of n, then we have to, so there are 2 to the power n principal minors. And if A and B have same principal minors, then we say that A is equivalent to B. So here is an example of two matrices A and B such that their principal minors are same. So in the last bullet point, for each subset, this contains what is the principal minor corresponding to that subset. We will again see this example after a few slides. So now I will present two applications of this problem. The first one is related to determinantal point processes. A determinantal point process on a subset of integers 1 to n is a random subset Y such that there exists a matrix A that satisfies this property. So this property says that for a given subset S, the probability that this random subset Y contains S is equal to the principal minor corresponding to the set S. And such a matrix is called kernel for this determinantal point process. Determinantal point processes have various applications in machine learning, which includes recommender systems, image search and segmentation, and audio signal processing. So now suppose the question asks that given there are two matrices and we have to decide whether.
Can you explain why this is useful in recommender systems and all of these things?
So for this, for recommender systems, suppose there are n objects and there are n objects and we have to decide what subset of objects to be recommended to the users. Then somehow we create a n cross n matrix such that the I comma jth entry represents the similarity between I and jth object, and then it is somehow that a subset of S is recommended to the user with the probability that the equal to the principal minor corresponding to this subset S.
So the point is to enhance diversity. Oh, sorry. So the determinants role of making a volume. So it's think of the point as vectors.
Oh, I see.
Then you're trying to maximize the volume of
Okay.
the like if all the points that you're choosing are very close together, then the volume that there will be very small. The determinant will be very small.
But
Also slightly or polished.
But my point was that this function, determinant of A minor S, it may not even be monotone decreasing in S.
So
And-
that's why we are saying that this matrix A is called, there exists such matrix A. So it has some properties which is like based on their eigenvalues lie between 0 and 1. Some properties have to be satisfied by the matrix to be a kernel of a determinantal point process.
And you are saying that the similarity matrix that you're talking about satisfies all those properties without.
Yes.
No, but such a thing has to be.
Usually also the square because it will be like a transpose type thing. So it will look like so then the non-negative will be imposed. Like
No, but if S1 is a subset of S2, doesn't this require you the determinant of AS1?
yes, so you need that
Yeah.
there has to be negative correlation.
There has to be negative.
So one non-trivial example of the thing is spanning trees. Random spanning trees have this property that the breadth of matrix will be.
Okay.
So,
So there are two issues. Certainly not all distributions on sets are DPPs. That's
anything like this already has negative situation.
And the other one is not all matrices give rise to.
No, yeah, because of this, not all of them. Yeah. But there are some do, for example, with the spanning distribution can be from this way.
Okay.
Yeah, if I remember, yeah, all of them will have negative association.
Okay. In fact, that was my next question. What is the necessary and sufficient condition for a matrix to be a kernel of a DPP, and what is the property of a distribution such that it can for it to be a DPP?
So I think if the eigenvalues are between 0 and 1, then can be shown that it is a kernel of a determinantal point process.
You're
That's
saying this is necessary and sufficient?
yes, I think. Actually, I'm not sure, but
Okay. Okay, let's go ahead.
Okay, so another application is related to polynomial identity testing.
And just another point about this.
Well, because it's like you look at so point process are things where you get some points, and for every subset you so like for the simplest level is a Poisson point process. So you see. No, you don't see me.
No, but completely.
Yeah. So the point is that like so your realization is some set of points. Okay, but this is not giving you the probability of a particular set of points. Just telling you what is the probability that a particular subset will be there. So things that are defined in this. So usually the point is that there will be some sort of independent kernel that every point comes up, and then whether it's successful or not will depend upon this extra kernel.
Yeah.
In case of the problem, it's some multiplication. Yeah.
Okay. So yeah, sure. So next application is related to polynomial identity testing. So in polynomial identity testing, the input is a polynomial from a class of polynomials, and the goal is to check whether it is 0 or not. So here input can be given in two different settings. The first one is black box setting, where the input polynomial is given by an oracle. Here the oracle takes as input a point, and it returns the evaluation of that polynomial at that point. And in the white box setting, the polynomial might be given via some explicit representations like algebraic circuit, algebraic branching programs, or symbolic matrices. So for this talk, the input will be given via symbolic matrices. So what is symbolic matrix? So it is a matrix that has linear forms as its entries, and the determinant of that symbolic matrix is called symbolic determinant. And since the entries of the matrix are linear forms, the variables can be separated, and the matrix A can be written as sum of variable times some matrix that does not contain whose entries are just elements over the field. So there a randomized algorithm for this PIT problem directly follows from PIT lemma, which states that if we take a random point, then a non-zero polynomial evaluates to non-zero with very high probability. A very big open question is to give a deterministic algorithm for polynomial identity testing. And this is known for some special classes of polynomials. And in this work, we give a PIT for some class, which I will define in the next few slides. So the class is related to symbolic determinant with rank 1 constraint. So here we define this class of polynomials parameterized by two variables n and m. It consists of all the polynomials which can be represented as determinant of symbolic matrices such that the matrix coefficients have rank 1. And now if the number of this matrix coefficients is polynomially bounded in the dimension of the matrix, then we call this class det1. Polynomial identity testing for this class is known to capture some combinatorial problems like bipartite perfect matching, linear matroid intersection, and full matrix rank completion. PIT algorithm for this class is known already. So the white box, in the white box setting, it was given by Loewy in 1989, and in the black box setting, it was a PIT algorithm was given by Gurjar and Thiruf in 2018. Now we will see how PIT for this class captures the problem of bipartite perfect matching.
Roshan, the PIT that is known due to Gurjar theorem, that's an n to the log n algorithm.
Yes, it's a quasi polynomial time algorithm.
Okay, and the Loewy algorithm is polynomial time, is it?
Yes.
Okay.
Do you give a better algorithm than Gurjar and Thirov?
No, so I'm just saying that this our polynomial is related to this class of polynomials.
Oh,
So
okay.
this is not exactly polynomials for this class.
Okay, got it.
So suppose this here is a bipartite graph on the left hand side and the corresponding symbolic matrix on the right hand side. For each vertex on the left hand side, there is a row, and for each vertex on the right hand side, there is a corresponding column. And for each edge of this graph, there is a corresponding variable. So suppose, for example, 1b is an edge, then there is a variable x1b in the row corresponding to first vertex and column corresponding to vertex b. Now if we compute determinant of this matrix AZ, then it turns out to be this polynomial. And if we closely look at this polynomial, then each of the monomial correspond to a perfect matching in the bipartite graph. So for example, 1b, 2c, and 3a forms a perfect matching in the bipartite graph. And here is the corresponding monomial, similar for this other monomial. And there is a one-to-one correspondence between perfect matching of the bipartite graph and the monomials of this polynomial. Now, if we separate the variables of symbolic matrix AZ, then this matrix coefficients has only a single non-zero entry. That implies that these matrix coefficients have rank 1. And since there is one-to-one correspondence between the monomials of this polynomial and the perfect matching, a bipartite graph has a perfect matching if and only if the determinant of this symbolic matrix is non-zero.
So Roshan, there should be a minus sign there, right?
So here we are assuming that this is over binary field.
Okay. Oh.
And now we consider the PIT for polynomials, sum of two polynomials which belong to this class, that one. So here is the problem. So we are given two matrices A and B, symbolic matrices, such that the matrix coefficients AIs and BIs have rank 1, and the goal is to check whether the sum of det A and det B is 0 or not, or in other words, whether determinant of symbolic matrix A is equal to determinant of symbolic matrix B. So this problem captures the problem of checking whether if two bipartite graphs G1 and G2 have same set of perfect matchings or not. So in the previous slide, I discussed that each of the monomials correspond to the perfect matching the bipartite graph. So the input graphs Gn and G1 and G2 have same set of perfect matchings if and only if determinant of the symbolic matrix corresponding to graph G1 is same as the determinant of the symbolic matrix corresponding to graph G2. So for the polynomials from this class state 1, actually it is known that what are the exactly coefficients of the monomials. So suppose this P is a polynomial which is represented as determinant of sum of AI times yi, such that the matrix coefficients AIs have rank 1. Now, since each AI has rank 1, it can be written as dot product of two vectors. And let U and V denote n cross m matrix such that the ith column is UI, of U is UI, and the ith column of V is VI. Then for any subset T of the set of integers 1 to m of size n, the coefficient of monomial, which is product of all the variables present in the set T, is product of determinant of submatrix UT and submatrix of V corresponding to set T. So this PIT problem reduces to checking given two pairs of matrices, so say U1 V1 and U2 V2. We have to check whether for all subsets T, this product is same for both these pairs. And this problem captures the problem of given two pairs of binary matroids given via matrices, whether these two pairs of matroids have same common basis or not.
Can you just hang on 1 second? I didn't quite understand. Can you just go back?
What's the binary method?
So binary matroid is like a matroid which can be represented. It is a linear matroid, and it can be represented over field F2.
So it is theorem. I didn't follow.
So why they have same common basis? Because here the coefficients will be either 1 or 0, and if this product is 1, then it says that T is a base of the common base of matroid represented by U1 and V1.
No, but in the theorem, what do the Y's have to do with the U's and the V's? Why should they be equal?
So I'm saying that this problem reduces to this problem is equivalent to checking whether this product is same for these pairs U1 V1 and U2 V2.
The theorem
because these are the only coefficients which are non-zero, and it corresponds to subsets T of size n.
So the theorem just states that if P is the determinant of such a matrix, okay, then the coefficient of any monomial in Y that you care about is precisely the product of the two determinants.
Okay, yeah, sure, okay.
Okay. So now we make this claim that PIT for sum of two polynomials from class state 1 is an reduces to an instance of equivalence testing of principal minors. So in the last slide I discussed that the sum of determinant of two polynomials from class state 1 can be represented by a pair of matrix. So now we have for each symbolic matrix we have a pair of matrices and the corresponding polynomial is P1 and P2. And now the goal is to check whether this product of determinant of some matrices of U1 and V1 is same as the product of determinant of some matrices of U2 and V2 for all subsets T.
Roshan, so we are in the setup where the PIT you're looking at is a white box PIT, and which is why you can figure out what U1, V1, U2, V2 are.
Yes.
Okay.
What is P1 and P2 here?
Yeah.
P1 P2 is the corresponding polynomial with respect to this pair of matrices U1, V1 and U2, V2.
It's like UV transpose. You look at the matrix UV transpose, right? And get instrument.
Yeah, UYV transpose.
There's no Y. I think just UV transpose and check that all the instruments are equal. So all the equal.
Oh, that's what, yeah.
So here is a brief proof idea. So first we find any subset T naught such that this product of determinant of some matrix is non-zero, and this is equivalent to the problem of linear matroid intersection, and there exists a polynomial time algorithm for that. So first we find T naught, and then we check whether this product is same for pair U2 and V2, and if it is not same, then these two polynomials P1 and P2 are not equal. And suppose if we find that they are same, so without loss of generality, we can assume that the sum matrix corresponding to the subset T naught is the identity matrix for U1, V1 and U2, V2. And hence we can write UI as something like this, and VIs as this for I belong to 1 and 2. And now it can be shown that this P1 is equal to P2 if and only if this M cross M.
I'm getting confused. So when you say it's equivalence testing of principal minors, the matrices were A and B. Now they're U and V. Is that what the connection is, or?
So now the matrices that we have to test is this matrix.
But why not just take U1, V1 transpose and U2, V2 transpose?
Yeah, so why will that not work?
No. So that doesn't work because that is checking. Here you have to check product of two guys.
Yeah, but that was.
So in that case, we are the coefficients will be principal minors of size n, not every principal minor.
All of them. No, but that's not going to happen. Right? So U is what? N cross M. U is N cross M. V is
Also N cross N, no?
yeah. So that's why U transpose. So N cross N. Oh, but you only want to check it for no.
So we have to check principal minors for corresponding to all subsets. So that will, I think, give us that we will. We have
Only one of them, man.
So if we had taken whatever U1, V1 transpose and U2, V2 transpose,
yes.
Does it only check if certain sized subsets are going to be equal? What happens there?
No, I still don't. Why is the minor of U V transpose the same as the product of the The
So
product
it
of.
will be like it will you V transpose, then it is sum of principal minors of size n.
Oh, it's already a sum of principal minors.
Yes.
Because it's summing over entry.
No. So I mean, it will basically be a sum of determinant of this guy and I mean UT and BT, but some those are all
And
possible.
do you see that those are not equal? The thing is.
For the full determinant, it's equal. For all subminors also, it's a.
Yeah, that's what wondering because it's like zeroing out certain growth rate. But maybe not. Maybe that doesn't work. It probably does. Yeah, because zeroing out is probably this.
So we have to check this product condition for each principal minor. If you just take U1 V1 transpose, then it will be sum of all these terms.
Yeah, sorry.
Okay.
So
The-
you're writing, you're now producing two matrices such that their minors are exactly the product of these determinants.
Yes.
Yeah. And
So
are these two matrices which you have produced.
yes. Because what will turn out that the only minors which are non-zero that will correspond to the that will have this value equal to this product, and all other minors will be zero for this matrix.
Or the principal. Yeah.
You only care about principal. No?
Yes. So this is the application of principal minor equivalence testing for PIT for some of two polynomials from det1 class. Now I will come back to our problem, and first we will see some operation on matrices that preserves principal minors. So one easy operation is just taking transpose of the matrix, and this second operation is obtained by the matrix is obtained by multiplying the matrix from left hand side with a diagonal matrix and its inverse on the right hand side. This diagonal matrix has to be invertible. So why they have same principal minors?
With those kind of matrices. So if I have just this 2 cross 2 blocks, so let's say just 1, 1, 1, 1 and 1, 1, 1, 1. So it's a 4 cross 4 matrix, and there are just these two all ones blocks sitting on the anti-diagonal. Okay. Now I can take just the corner one entry of the lower block and the whole thing of the second block, and that's the principal minor, right? Because I'm taking the same set of rows and columns. I'm taking the first 3 rows and the first 3.
So are you saying that this matrix, the matrix that you have taken is a permutation matrix?
Yeah. It was diagonal. Yeah. Use the same set, some of them.
Can you repeat the question?
No, I think it was settled. Yeah, you can go ahead.
Okay.
If the two sets are equal, then there will be this large zero submatrix sitting in the
Determinant, yes.
Okay. So here is why this matrix A and dA times D inverse have same principal minors. So consider any permutation from the set of integers 1 to n to the set of integers 1 to n. So the term corresponding to this permutation for matrix A will be this, and the term corresponding to this permutation for this other matrix dA times D inverse will be this, and this part is same for both the matrices. And if we go through 1 to n, then each of these index from 1 to n will occur exactly once, and hence they will cancel out. So they have same determinant, and this is true for all principal submatrices, hence they have same principal minors. So here is an example that we saw in the first slide. So actually here, this matrix B is DA A times D inverse, where this D is a diagonal, invertible diagonal matrix whose entries are 1, half, and -1. A natural question to ask is that, are these two operations sufficient to describe any another matrix B which has same principal minors as A? So this is true.
Question, I didn't follow the argument why diagonally equal matrices are
Have same determinant.
the same determinant is fine. Are you saying
Ah.
that all minors are the same?
All the
All
principal.
principal minors are?
So because this is like saying that the ith row is scaled by D1.
Oh, once again,
etc. And you are unscaling them with respect to the columns.
once again,
Any principal submatrix can of DA D inverse can be written as the diagonal in, if it take the diagonal submatrix of diagonal matrix corresponding to those entries.
got it.
Okay.
You apply the same result to the everything outside this set.
Yeah.
Yeah.
And these two operations are sufficient when the input matrices are from a certain class of irreducible matrices. Irreducible matrices I will define in the next slide. So we say that a matrix A is reducible if there exists a permutation matrix P such that PAP is a block upper triangular matrix. Or in other words, if we can permute rows and the corresponding columns, then we get a block upper triangular matrix. And if a matrix is not reducible, then it is called an irreducible matrix. So here is an example of reducible matrix. Now, if we exchange second row and column with a third row and column of A, we get this following matrix, which is block upper triangular. For a block upper triangular matrix A, whose index set is partitioned into, say, T1 through Tk, such that the blocks are AT1, AT2, and so on, then its determinant can be written as product of these blocks, such that, and now all these blocks will be irreducible. For this matrix A given in this example, any another matrix B will have same principal minors if the principal submatrix of A corresponding to set 1, 3 is principal minor equivalent to the principal submatrix of B corresponding to set 1, 3. Similar for the set 2 and 4. So because since this is upper triangular matrix, only these entries matter. In 1984, Hartfield and Loewy showed that the principal minor equivalence testing problem for general matrices reduces to the problem of principal minor equivalence testing for irreducible matrices. Now I will talk about some results known for principal minor equivalence testing for irreducible matrices with some constraints. So here is for a matrix n cross n matrix A, a subset S of size at least 2 and size at most n-2 is called a cut if these two submatrices have rank at most 1. So here is an example of a matrix with a cut. For this matrix, the set 1, T is a cut because if you take this submatrix, it has rank 1, and similarly this submatrix has rank 1. because it can be written as dot product of two vectors. In 1980, Engel and Snyder showed that for an irreducible symmetric matrix A, another matrix B has same principal minor if and only if this B is diagonally equal to A or B is diagonally equal to this transpose of matrix A.
But for symmetric, it wouldn't matter, right?
What do you mean?
The symmetric matrix A transpose is just A, no?
Yes.
Okay.
Yeah. For reducible matrices with no cuts, a similar result was shown by Raphael and Loewy, where they showed that another matrix B has same principal minor if B is diagonally equal to A or its transpose. And in last year, Ahmadiyya showed that if a matrix has a cut, then she gave a procedure to generate another matrix which has same principal minor, but it is not diagonally equal to the input matrix or its transpose. And this construction follows from this idea. So given a matrix with a cut, now we'll discuss what is its determinant. So suppose A is an irreducible matrix with cut S. Here, the text in blue represents the index of rows and columns. And since S is a cut, this submatrix has rank 1. These two submatrices have rank 1 and can be written as dot product of two vectors. So for computing this determinant, we use the generalized Laplace theorem, which shows that for a matrix P, if and we fix a subset S, then this determinant P is sum of these terms, where each of this summand corresponds to a subset T whose size is same as S, and the summand corresponding to set S is product of determinant of submatrices corresponding to set S and T and complement of sets S and T. And this is some sign function which depends on sets S and T. And now if we compute determinant of this matrix A using generalized Laplace theorem, so the first term corresponds to the term when this T is exactly equal to S. So when T is exactly equal to S, then this is the matrix P, and this matrix is equal to matrix N. And now we consider subsets S dash which can be which differs from S by one element. So I claim that for any other terms, this will be equal to 0, because if it differs from S by more than one element, then two rows, there will exist two rows which can be written as a multiple of each other. So that's why it will contribute 0 to this sum. It can be shown that this second term can be written as product of determinant of these two matrices. And Ahmadiyya presented this operation. This name was, and we call this operation twist because of following reason. So now we have input matrix which has a cut S. From the previous slide, its determinant can be written as this. Now we define twist of matrix A with respect to cut S to be this following matrix. So here M remains the same. We take transpose of matrix N and we exchange Q and U with each other. Now, since this matrix that is twist with respect to cut S has similar structure as A, its determinant can be written as like this. And here this matrix is transpose of N, and this matrix is transpose of this matrix. So they have same determinant. And now if we take any principal submatrix, they will have same structure as A, and the twist of A is the submatrix of A, and the twist of A with respect to cut S will have same structures, and hence they will have same principal minors.
Roshan, can you go to the previous slide? Sorry.
Okay.
So I was wondering if there is a graph theoretic interpretation for this. So one of the things that you had mentioned was that if you have two, a related problem is you're given two graphs and you want to check if the set of matchings in these graphs are the same.
Yes.
Do these things tell you how you can convert one bipartite graph into another while, I don't know, somehow retaining the set of matchings or something? Is there a combinatorial interpretation of this? And also, why is it called a cut? That also felt like there probably is some combinatorial interpretation.
So actually there are also some different names. That is something like H clan or something. Ahmadiyya used this term. She defined this to be a cut. So we are just using her notation.
Okay. Okay, but do you know of any graph theoretic interpretation of this?
So from this bipartite matching, so it is like first we find a common matching into these two graphs. Then this the matrix that we get, for which we have to test principal minor equivalence, that will correspond to this augmented cycles in the bipartite graph. And the principal minor for this principal minor equivalence testing for this case will be checking this whether they have same set of cycles or not. And this twist operation will say that how we can get from this how we can change this structure such that this set of cycles remains same in augmented cycles remain same in this bipartite graphs.
See, I don't see it, but okay, I can check with you later. Yeah.
Okay. Now we ask this, that whether these three operations is sufficient to represent any matrix which has same principal minors. So now in this work we show that yes, these three operations are sufficient. So formally we show this theorem that suppose we are given two matrices A, irreducible matrices A and B, which have same principal minors, then there exists a sequence of matrices A0, A1 through AK, such that A0 is equal to A, such that the ith matrix in this sequence is obtained by twisting its predecessor matrix AI minus 1 with respect to one of its cut xi, and the final matrix AK is diagonally equal to B or transpose of B. And actually we also gave a polynomial time algorithm that given if the input matrices A and B have same principal minors, then we output a sequence of then we output this sequence such that the number of matrices in this sequence is less than 2n, and if the principal minors are not same for the input matrices, then we output a subset S such that the corresponding principal minor of A and B are not same.
Sorry, so in your second theorem, the sequence of matrices is similar to what you have in the first theorem. That is, it tells you how to transpose A to B. Okay.
Yeah, so this is kind of like a certificate that they have same principal minors.
And does this assume that A and B are irreducible, or it works for any A and B?
Yeah, so here we assume that these input matrices are irreducible.
In the second theorem also.
Yes.
Irreducible decomposition.
Because if the matrix is irreducible, then finally we are transforming to some smaller instances of principal minor equivalence testing for irreducible matrices.
Okay.
So irreducibility has strongly connected components in there.
Yeah.
What is cut thing say because the graph at SC matrix, isn't it something like that every node in S has the same set of essentially same set of neighbors in S?
Yes.
Except that some things might not be neighbors at all, and similarly for S. But it does not look like a cut. But it,
Yeah, it doesn't look like a cut. I don't know what that.
it's a strange thing. It's like a collapsed vertex kind of.
I mean, reducibility does feel like it's like saying that your bipartite graph has these two blocks, and the edges either go parallel or below. It's like there is no edges going this way.
Reducibility is strong there.
Yeah, and reducibility somehow reduces the act of searching for a matching as you search for a matching here and then you do this.
So one thing is that suppose if we take the matrix corresponding to bipartite matching, and if we apply this twist operation, then it might happen that the matrix that we get now does not correspond to a bipartite instance of bipartite matching.
Oh.
Yes. So because you might remember that there was this specific representation of these matrices where this top left and right bottom matrices are the zero matrix. So now if we apply cut operation, this condition might be violated, and it is not clear how to get back the bipartite graph from this matrix. Now so in this talk, I will briefly discuss the proof idea of this theorem and then give an overview of the algorithm. For this talk, I will assume that the entries of the matrices are off-diagonal entries of matrices are non-zero. And in our work, we saw that if we show the theorem for this case, then it implies this theorem for irreducible matrices also. And this is a common technique that has been also used in previous works. To prove our theorem, first we require some properties of minimal cut, which I will define in this slide. For here is again this definition of cut. For an n cross n matrix A, a subset S is called a cut if these two principal submatrices have rank 1. And now we say that S is a minimal cut if there does not exist any cut T, which is a proper subset of S. So here is one property of minimal cut, that if S is a minimal cut of A, then for any T which does not belong to this set S, the principal submatrix corresponding to set S plus T does not have any cut. So we show this by contradiction. Suppose this is not true, and X is a cut of this principal submatrix corresponding to set S plus T. So here this text in blue represent the index of columns and rows. And now suppose in the column T, the vector corresponding to rows indexed by set S minus X is U1, and similarly the vector corresponding to set X minus T is U2. Since S is a cut, this matrix and this and we from our assumption that the off diagonal entries are non-zero, this matrix should look something like dot product of U1 times some another vector. And similarly, this matrix should look like dot product of U2 with some other vector. And now, from our assumption that X is a cut of this principal sum matrix S plus T, this should also look like dot product of U1 with some vector V1. Similarly, we consider the row corresponding to index T, and suppose this vector corresponding to columns indexed by set S minus X is Q1, and similarly Q2 correspond to the columns corresponding to index X minus T. Following the same argument, we can say that the remaining entries of the matrix should look like this. But now what happens that if we consider this set S minus X, then it turns out to be a cut of this matrix A. So because if we consider this submatrix corresponding to set S minus X and its complement, it is dot product of U1 times this concatenation of V1, 1 and V2. And similarly for this another submatrix. So this contradicts the minimality of cut S. So this completes the proof of this lemma. Now here is another property of minimal cut. So suppose these two reducible matrices A and B have same principal minors, and the size of this cut is greater than 3, then we can show that S is also a cut of this matrix B. From the previous claim, for all the T's which is not present in S, the principal submatrix corresponding to this set S plus T has no cuts. From the result of Raphael and Loewy, since these matrices have same principal minors, they must be diagonally equal. This matrix, principal submatrix of B corresponding to set S plus T, must be diagonally equal to principal submatrix of A corresponding to set S plus T, or its transpose. So here it's transpose. So a brief proof idea for this is that we fix some element T0 which is not present in S, and without loss of generality we can assume that this D is the identity matrix, and hence this principal submatrix corresponding to set S plus T0 is same for A and B. And now if we take a look at the principal submatrix of A corresponding to set S plus T0 and T, where T is some element which does not belong to S and it's different from T0. So it looks like something like this. Since S is a cut, this column vector should be some multiple of P, and similarly this entry should be a multiple of this Q transpose, and this structure is same from our assumption. And now we will argue that how X and Y transpose will look like. And since from this claim, this principal submatrix of A corresponding to S plus T does not have any cut, so and it is irreducible, so it should the principal submatrix of B corresponding to set S plus T must be diagonally equal to principal submatrix of A corresponding to set S plus T or its transpose. So suppose we take the first case, whether it is diagonally equal to the submatrix, then from this it follows that X is also some scalar multiple of vector P and Y is some scalar multiple of Q. So, and this will be true for all T's which are not present in S. So this will show that S is also a cut of matrix P. Now we'll give a proof of this proof idea for our theorem. So here I am again reiterating the theorem, which says that if two matrices A and irreducible matrices A and B have same principal minors, then there exists a sequence of matrices such that the ith matrix in the sequence is obtained by twisting its predecessor with some of its cut, and the final matrix is diagonally equal to B or its B transpose. So the base case is that if this matrix A has no cut, then from the result of Raphael and Loewy, B must be diagonally equal to A or its transpose. So here, in this case, the sequence has only one matrix. Now suppose if the matrix A has some cut, then we show this lemma, which says that if S is a cut of matrix A such that T belongs to this set S, and X is a cut of principal submatrix corresponding to set S complement plus T, then in the bigger matrix A, there is also exist a cut T such that, so here suppose B is this matrix obtained by twisting A with respect to cut T, such that in the B, if we consider the principal minor corresponding to set S complement plus T, then it will be same as the matrix obtained by twisting principal submatrix A with respect to cut X. And another thing is that if S is a minimal cut of this matrix A, then it will remain a minimal cut of matrix that is obtained by twisting A with respect to cut T. So now we are assuming that there exists a cut in the matrix A and S is a minimal cut. So by induction hypothesis, since A and B has same principal minors, we will apply our theorem for principal submatrix corresponding to set S complement plus T, and then we will get a sequence of submatrices such that the end matrix is diagonally equal to principal submatrix corresponding to S complement plus T or its transpose for this matrix P. Here is again the lemma that was stated in the previous slide. And now we continuously use this lemma on repeat to get the sequence of matrices A0 through AK such that this AI is obtained by twisting AI minus 1 with respect to cut TI, such that the principal submatrix of AI with respect to S complement plus T is same as this matrix A dash I, and S is also minimal cut of matrix AI. So now from this, what we get that we have a matrix AK, for which the principal submatrix corresponding to this set is diagonally equal to principal submatrix of B with corresponding to that set or its transpose. And finally, we also get that this matrix AK also has this minimal cut S as its minimal cut. So now to complete the proof of theorem, we just have to find sequence from AK to B. So now we can assume that we have this matrix A which has same principal minors and B, and we have a minimal cut S which is also common to B, and we have an index T0 in S such that the principal submatrix corresponding to this set S complement plus T is same. So now we saw that if these matrices A and B satisfy this condition, then B is either diagonally equal to A, or the matrix obtained by twisting A with respect to cut S complement. And the proof idea for this is that if S is a minimal cut of A, then for all T which is not present in S, this principal submatrix corresponding to set S plus T is irreducible. And from the theorem of Raphael and Loewy, if principal submatrix corresponding to S plus T is irreducible, then it does not have any cut, and it is diagonally equal to either principal submatrix of B corresponding to set S plus T. Then in this case, what will happen that B is diagonally equal to A, and in the other case, it happens that B will be diagonally equal to twist of matrix A obtained by twisting A with respect to cut S complement. So this completes the proof of the theorem. So now in the next slide, I will combine all these ideas and give the overview of our algorithm. So first, we will check if A has cut or not. So if A does not have a cut, then we just have to check whether A is diagonally equal to B or B transpose. Otherwise, we will find a minimal cut S in A. Then we fix some index T0 in set S and recursively check for the principal minor equivalence for this submatrices of A and B corresponding to set S complement plus T0.
By the way, Roshan, try to wrap up soon. You're over time.
Yeah, sure. That's okay. So now we get the sequence for this pair of submatrices, and from this sequence we generate a sequence from A to A dash, such that the principal submatrix corresponding to this set is same for A dash and B. And now at the end we will just check if B is diagonally equal to A dash, or the matrix obtained by twisting A dash with respect to cut S complement. So this is the algorithm. And now I will talk about related open problems. One problem related to this is called principal minor assignment problem. Here we are given, here there is an unknown n cross n matrix A, and the input is an oracle that outputs that takes as input a subset S and outputs the principal subminor corresponding to that set S. And the goal is to find any matrix B using polynomially many queries to the oracles such that it has same principal minors as A. And results are known for some special classes of matrices. And fortunately, the results are known for those classes for which principal minor equivalence testing was known earlier. So now we hope to solve this problem for general class.
Roshan, for this problem,
Yes.
the sense, is it okay? Possibly, or is something you mentioned earlier. Can the description of a equivalent matrix in this sense just be obtained by knowing polynomially many det ASs, or
Yes, so in this problem we have to make only polynomially many queries.
so is it clear that that's sufficient? Forget about. I'm not asking polynomial time. I'm just asking query complexity. After making queries, can you identify which an equivalent matrix already?
Existing could happen that there are two A and B where they agree on any polynomial size.
Yeah, so that question should first be true before.
So here we, so in our setting, we know what these matrices look like, but here we don't know. So I don't know.
Just to phrase Pralad's question differently, there are 2 to the n possible principal minors you could ask for.
Yes.
Somehow you are saying that by making just poly n queries, I mean, if you are able to figure out a matrix B, then it basically means that you are able to infer the value of all the other 2 to the n minus poly n minors that you didn't even query for.
Yes. So for this special classes of matrices, most of the results is like they have shown that for some constant number, if we check all the principal minors of that size, then that is sufficient to get this whole matrix P. For this, whatever the results are known, it follows something like that.
But that is like, so there's one positive thing, if you have sums at all levels, then you have the eigenvalues.
Yeah.
But I think those matrices are those where you just know like some of eigenvalues, maybe some of square something, you know all the eigenvalues. Right? So therefore, like if you only know minus at a certain level, then you only know the first three coefficient of the type.
So, but eigenvalues is also something like a set, right? But whereas here you care about the principal minor, like in terms of the orientation and something. Like in the sense that eigenvalues stay the same even if you did similar
Some
matrices.
things, yeah. So,
But
it must be.
yeah.
But
you will see why the.
but the things you're saying there, even the eigenvalues matching is a pretty big thing. Because
Yeah,
the thing is some few coefficients are matching. Yes.
But why is this surprising? A matrix only has n square entries, right? So why is
No.
everything's done by n square entries? So this
No, that I agree, but. No, so I would like to see a theorem statement of, so I won't be surprised, but I would like to see the theorem statement, but can I identify the class by just querying so many guys?
I mean, but I guess Raghuvansh's point is that if you didn't care about efficiency,
Hmm.
the fact that there are n squared of these values that determine all the other values, that by itself should not be surprised.
No, that's true, that's because all these DPPs have a concise description, they have an n square description.
Yeah.
But if you're just you're allowed to only query these guys, is it clear? If you're querying those n square guys, yes, there is this one. If you're only
These, what do you mean by these guys?
you're only wants determinant of principal minors.
No, that's what Raghuvansh is saying. He's saying that
Yeah.
the set of all possible things, there is some n squared thing that generates the space. The generation could be terrible. It's some horrible, complicated constraints. I mean, eventually, whatever the principal minors are, there are some functions of n squared things.
Agreed, yes.
So there must be n squared of these things, which are sort of algebraically independent or something.
That's not clear.
That's not clear. That's another thing. That could be separate.
No, I agree, but what I want is a theorem that says that, yeah, that's basically my, it's not surprise. I won't be surprised, but I would like this.
This is an old joke that like someone says in class that this is trivial. Someone asks why is it trivial? And then this person walks around for 10 minutes. It's so trivial.
I wasn't that one. Maybe I told you this.
I read this many years ago.
No, okay, it happened.
It's not easy to understand, you already, yeah, go ahead.
Okay. So we have in this work we gave a white box PIT for sum of two polynomials from this class state one. So related question could be to give a black box PIT for this for sum of two polynomials from class state one. And now we can generalize this PIT problem and take sum of some constant many polynomials from this class state one and ask whether its sum is 0 or not. And yeah, so these are the related open problems to this problem. Thank you.
Any more questions for Roshan? Okay, let's thank him again.
Okay. So I will stop presenting now.
Okay, thank you, Roshan. I'm going to end the call now, and we'll reach out.
Okay.
Okay, bye.
Bye.
See you later. Bye. You can see him now.
The video is fine here.
You can see the speakers too.
Okay, thank you.
Bye.